Hello and welcome to Algebra 1, Lesson 11. In this video, we're going to start talking about how to solve linear inequalities. So this lesson is going to be all about learning how to solve a linear inequality in one variable. Now, the procedure is basically the same as with solving a linear equation in one variable, but with a few key differences. So let's start out today by just reviewing some basics about inequalities. So the first thing is that this symbol right here, it points to the left. It's known as the less than symbol. Then this symbol right here that points to the left with a bar underneath it is the less than or equal to. This type of inequality is known as a strict inequality. So something is strictly less than. This type of inequality is known as a non-strict inequality. So it allows for the possibility that they're equal, right? It says or equal to, right? In this case, it's strictly less than. In this case, it's less than or equal to. Now we also have the greater than. This points to the right. And then we have the greater than or equal to. Points to the right but has a bar underneath it. And again, this greater than is a strict inequality. This is a strict inequality. Strictly greater than. This type of inequality, this greater than or equal to, is a non-strict. That's because we allow for this or equal to. So again, the symbols less than and greater than are referred to as strict inequalities. Then the symbols less than or equal to and greater than or equal to are known as non-strict inequalities. Very important that you understand the difference between the two. So in order to start thinking about inequalities in the right way, I want you to first think about a basic equation. Let's say we have something like x equals 2. So if I was to graph x equals 2 using this basic number line, what I would do is I would take and I would put a filled in dot or filled in circle, however you want to think about that, specifically at the number 2 on the number line. If I had something different, let's say I had x equals 5, for example. Let me do this in a different color so that we don't get confused. So let's say I had x equals 5. Well, I would graph that by putting a filled in dot or a filled in circle at 5. That's my solution. Let's look at one more. Let's say we had x equals negative 3. Well, I'd put in, again, a filled in dot or a filled in circle at negative 3. So in each case, we're showing a visual representation of the solution to the equation. And this is going to get much more complex as we go throughout algebra. For right now, this is about as basic as it gets. What about x is greater than 2? How would I graph that? Well, we're going to come back to this, but I just want you to realize that in the case of an equation, we have an exact number. It's kind of a laser focus. It's x has to be 2. It's equal to 2. In this case, where we have x is greater than 2, we're now thinking about a range of values because x can really be anything larger than 2, and this is a true statement, right? If I replaced x with, let's say, 7, and I had 7 is greater than 2, this is true, right? This is true because this 7 is greater than this number 2, so that's true. If I put something in that's 2 or lower than 2, it's going to be false. So like, for example, if I put in 2, that's false. 2 is not greater than 2. 2 is equal to 2. So this is false. Or if I put something much lower than 2, let's say, I don't know, negative 7. Negative 7 is not greater than 2. Again, this is false. So when we think about inequalities, our solution is generally going to be a range of values. So in order to deal with that, we have something known as interval notation. Let me just write that down. We have interval and then notation. And so this notation is going to specifically help us deal with a solution that's a range of values. Now, typically, the way you're going to write this, you're going to have your smallest value, then comma, your largest value. Now, it's not going to exactly work out this way because in a lot of cases, you're going to see you can't exactly put the smallest value because it's impossible for you to list it. So you're going to put something close to that, and then you're going to use a special type of notation. So let's kind of jump in and just think about x is greater than 2. This is what we saw before. If I want to use interval notation, what's the smallest possible value that x can take on? Well, it can't take on 2, but it could be anything larger than 2. If I think about what's the smallest number that you can think of that's larger than 2? Well, you might say, okay, 2.1. And then you could get smaller. You could say, okay, well, 2.00001. You could get smaller and say 2.00000000001. And you can keep doing that forever and ever and ever. So because you can't possibly list the smallest value that is larger than 2, you're just going to put 2 there. And you're going to place a parenthesis to the left of that to say that the 2 is not included. So it's not included in the solution. So when we look at this and we see it, we say, okay, the smallest value is anything larger than 2. Now, I'm going to put a comma. Now, if x is greater than 2, what's the largest value that x can take on? Well, in terms of numbers, there's really not one because numbers continue forever. Whatever the largest number is that you can think of, you can always add 1 and get to the next largest. So to kind of notate this concept, we use the infinity symbol. So the infinity symbol, and it kind of looks like a sideways 8. And because infinity is not a number, you're also going to put a parenthesis next to it to say that, hey, this is not included, right? It's not included. Now, we're going to see in a minute that we're going to have a different type of notation when things are included. So we see our interval notation for x is greater than 2. How do we use this to graph? Well, it's similar. If I have x is greater than 2, I find 2 on the number line. And what I'm going to do is I'm going to put a parenthesis at 2 that faces in the direction of my solution. So this is going to face to the right because everything larger than 2 is in the solution. The parenthesis is telling me that 2 is not included. Not included. And then I'm going to shade everything to the right. So I'm going to shade all this. And when you're doing this on a test, just make it clear that you're shading everything to the right. And just shade that arrow there just to say, hey, this is going to continue forever and ever and ever. Let's try another one. Let's say we had something like x is greater than 4. So x is greater than 4. So in interval notation, again, you want the smallest value on the left. Now, I can't possibly list the actual smallest value because, again, I can't get to it. Anything that I could list that's the smallest value could always get smaller. So I'm just going to go ahead and put 4. And I'm going to put a parenthesis next to 4 to say that it's not included. It's not included. But hey, anything larger than that is. So then I put my comma and then my largest value. And again, because x can be anything larger than 4, there is no largest value. So we're going to put the infinity symbol in. Again, it looks like a sideways 8. So we put our infinity symbol in. And again, we put a parenthesis to say, hey, it's not included. And then graphically, we're looking for 4 on the number line. We're going to put a parenthesis there at 4 to say, hey, 4 is not included. That means not included. And then we're going to highlight all this. And we're going to highlight that arrow to say, hey, this solution is going to continue forever and ever and ever in that right direction. So what about something like x is less than 5? Well, if I look at my number line here, I see 5 is here. So x can be anything less than 5. It can't be 5 itself, but any value lower than that. So if I was to notate this, what is my smallest value? What is my smallest value? Well, there's not going to be one, right? Because I can keep going to the left forever and ever and ever. So we're going to notate this using the concept of negative infinity, right? Just like we had positive infinity to say, hey, numbers increase forever and ever and ever going to the right. So with positive infinity, whatever number I can think of, I can always add 1 to get to the next largest. With negative infinity, whatever number I can think of, I can always subtract 1 and get to the next smallest, right? Numbers continue forever in the left direction as well when we think about a number line. So a negative infinity looks like this. You put a negative, and then you put your infinity symbol. Remember, that's just a sideways looking 8. Now, because infinity is a concept, infinity or negative infinity, it's not really a number, it's a concept, you can't really include it. So you're always going to use a parenthesis next to them. Okay, so I put a parenthesis there. Now, what's my largest value? What's my largest value? I know that x can be anything up to, but not including 5. So if I look at the number line, I can get as close to 5 as I want, but I can never touch 5. So because I can't really list that as an actual number, I'm just going to use the number 5, and then I'm going to put a parenthesis next to it to again say that, hey, this is not included. This is not included. So anything smaller than 5 works, but I can't actually use 5. And let me put this over here too, that this is not included. And then graphically, it's basically the same thing. Now I'm using a parenthesis at 5 to say that 5 is not included. But notice how now I'm going to point the parenthesis towards the left because my solution goes to the left. And now I'm just going to shade all of this and then make sure you shade that arrow in to say, hey, this is going to continue forever and ever and ever in the left direction. All right, so when we have a non-strict inequality, we're going to use a bracket next to the number that's included. So this is the biggest thing we need to remember. So now we're looking at x is greater than or equal to 2. Or equal to 2. Very important you understand the difference. So when I look at my number line, x can be 2 now. It can actually be equal to 2. That can be a solution. It can also be anything larger than 2, just like with the strict inequality. So in this particular case, when we're writing out our solution in interval notation, the smallest possible value that x can take on is actually 2. And I put a bracket there to say that 2 is included. Now, comma. Now, what's the largest value that x can take on? Well, again, it's going to be infinity, right? Just because I have a non-strict inequality doesn't mean that both of them are going to have a bracket. X is anything that is greater than or equal to 2. So x still goes out forever and ever and ever in the right direction. So we're going to use infinity here to notate that, and then you always put a parenthesis there. And again, this is not included. Okay? So now graphically, you're going to change things up a little bit. So at 2, instead of a parenthesis, you're putting a bracket. And that bracket faces in the direction of the solution. So that's going to face this way. And then I'm going to shade everything to the right, including that arrow, to say, hey, 2 is included. Is included. And then also anything to the right of 2. Okay, so 2 itself, and then anything to the right of 2, continuing out forever and ever and ever out to infinity. What about x is less than or equal to 5? So again, here's 5 on the number line. So now x can be 5 or anything less than 5. So when we think about writing our solution in interval notation, the smallest possible value is still the same. The smallest possible value is still negative infinity, right? Because we can have x as anything that's 5 or less. And that continues to the left forever and ever and ever. So we still have negative infinity, and we still use a parenthesis next to that to say, hey, this is not included. Then we have comma. Now what's the largest value that x can take on? Well, x can take on the value of 5 now, but nothing larger. So I'm going to put the number 5, and I'm going to put a bracket next to 5 to say that 5 is included. So basically what you need to take away from this is that a bracket tells you it's included, parenthesis tells you it's not included. And to graph this, again, very, very simple. You put a bracket at 5, and it's going to face in the direction of the solution region. So 5 is included, that's why we use the bracket. We just shade everything to the left. everything to the left, shade the arrow, because this continues forever and ever and ever in that direction. So again, the main takeaway here is that if you're using a parenthesis, you're saying that the number is not included. If you're using a bracket, you're saying it is included. Now, not to confuse you, but I want to cover something that your teacher or your textbook might do. So I want to erase this real quick, just the graphing part. Your teacher, your textbook, your tutor, whoever you're using to learn this information may do things a little bit differently. When you graph things, you can do it in the way that I showed you, perfectly legal, perfectly acceptable, or there's another way. Instead of using a bracket, when something's included, you use a filled in circle or a filled in dot. So this means is included. If something's not included, you can use an open circle or an open dot, meaning it's empty, it's not filled in. So this is not included. So for example, if x is less than or equal to 5, I could show that graphically by kind of making a filled in circle here and just going all the way to the left and highlighting this. This is the same as putting a bracket facing to the left and shading to the left. You may see this in your textbook. As another example, we go back and revisit x is less than 5. And so again, instead of this parenthesis here to say 5 is not included, what your teacher may do is put a circle at 5 that's not filled in. You see how there's a gap there? Let me make it a little bigger. Let me make it a little bit bigger. So let me just make that huge. And so you can see there's open or a non-filled in area there, and your teacher may show you that, right? So this means 5 is not included. If I filled it in, it means 5 is included. So I just want to bring that to your attention in case you're reading a book and it shows you a different way and you're like, where'd that come from? Why is he doing it this way? Both ways are accepted, and probably as you move higher, the way that I'm showing you now is more accepted or used more often. I wouldn't say more accepted, but used more often. All right, so now that we've gotten the basics out of the way, let's cover a few things that you're going to need to know to be successful with solving a linear inequality in one variable. So the first thing is called the addition property of inequality. And you'll recall that we had an addition property of equality. Well, this is just for inequalities now. So it tells us we can add or subtract any number to, or in the case of subtraction from, both sides of an inequality without changing the solution. So that property that we use to solve equations, where we added or subtracted the same number to or from both sides of the equation, can be extended to inequality. So we can now add or subtract the same number to or from both sides of an inequality. Now here's the other one, and this one is something you need to really pay attention to. We have the multiplication property of inequality. So I'm gonna give you two different scenarios here. We can multiply or divide both sides of an inequality by the same positive number. There's a reason I put this in red and bold. So positive number without changing the solution. So just like the multiplication property of equality, the stipulation there was same non-zero number, right? You could multiply both sides of an equation by the same non-zero number and you didn't change the solution. Here, what I'm telling you is that you can multiply or divide both sides of an inequality by the same positive number, and positive does not include 0, for those of you who are thinking that. 0 is not positive or negative, it's neither. So by the same positive number without changing the solution. Here's where we run into problems. And I can't tell you how many tests I've graded in my life, and I've seen students just not get this. If we use the multiplication property of inequality with a negative number, okay, something that is less than 0, we must reverse the direction of the inequality to preserve the solution. So if you multiply both sides of the inequality by the same negative number, flip the inequality. If you divide both sides of the inequality by the same negative number, flip the inequality. So before we move on and start solving problems, let's explore this concept more thoroughly. So let's start off with something very, very easy. Let's say I had 2 is less than 7. So at this point, we should all know that this is a true statement, right? This is a true statement. And what makes it true? Well, 2 is less than 7, right? 2 is a smaller value than 7. 2 is to the left of 7 on the number line. If I had something that said 2 is greater than 7, this would be false, right? 2 is not greater than 7. So that's the difference between a true and a false statement when you're dealing with an inequality. So beginning with a true statement like 2 is less than 7, we can begin to experiment a little bit. Let's say we think about our multiplication property of inequality. And let's say we multiply both sides of the inequality by the same positive number. Recall that this should have no effect on the direction of the inequality, right? The statement should remain true. So let's say I multiply both sides by the number 4. So I'll multiply the left by 4 and also the right by 4. So 4 times 2 is 8, and this should be less than 7 times 4, which is 28. And we can see we still have a true statement, right? 8 is less than 28, right? It's a smaller value. If I have $8 in my pocket, I certainly have less than if I had $28 in my pocket. Now let's think about something else. Again, starting with this same true statement, let's multiply both sides of the inequality by a negative now. So let's multiply both sides by negative 4. So times negative 4 over here and times negative 4 over here. Now negative 4 times 2 is now negative 8. And we're saying this is less than 7 times negative 4, which is negative 28. Now the statement is false. And a lot of you who haven't worked with integers a lot might be a little confused by that. But think about this for a second. Negative 8 is actually a larger value than negative 28, right? Negative 8 is not less than negative 28. And you kind of think about this involving the number line. Negative 8 is to the right of negative 28 on the number line. Negative 28 is to the left of negative 8 on the number line. You kind of think about that either way. And remember, if a number is larger than another, it lies to the right of it on the number line. And if a number is smaller than another, it lies to the left of it on the number line. So this is false. In order for us to get a true statement, again, when we multiply both sides by that same negative value, we have to flip the direction of the inequality. So if I would have flipped this here, instead of a less than, now I'd have a greater than, then we could say it's true. Then we could say it's true, right? Negative 8 is greater than negative 28. And let me show you one more example of this real quick before we move on. So again, let's start out with a true statement. Let's say I had something like 10 is greater than 5. Okay, so at this point, we all know this is true. Again, if I multiply both sides by the same positive value, we'll still have a true statement. So let's say we multiply both sides by positive 2. So positive 2 times 10 is greater than 5 times positive 2. And 2 times 10 is 20. And this is larger than or greater than 5 times 2, which is 10. Yeah, this is still true. Again, if I multiply both sides by the same negative value, in order for me to keep a true statement, I've got to reverse the direction of the inequality. So if we erase this and say, okay, so let's multiply both sides by negative 3. So let's multiply by negative 3 over here and by negative 3 over here. And we're just going to leave this as it is for now, and I'll show you that it's false. Negative 3 times 10 is negative 30. And we're saying this is greater than 5 times negative 3, which is negative 15. And again, now this is false, right? It doesn't work anymore. And one of the reasons you can kind of think about this is, okay, if I'm starting out with a bigger number, when I multiply it by a negative, I'm going to have a bigger negative, and a bigger negative is actually a smaller number, right? As numbers go this way, as the numbers get bigger and bigger in the negative direction, they're actually getting smaller. And I know, again, if you haven't had a lot of experience kind of thinking about integers in that way, it might be a little confusing, but just think about your number line, right? It looks like this. Here's 0, and as numbers move this way, right, you're getting smaller and smaller values. So in this case, negative 30 is greater than negative 15 would be false. In order for us to have gotten a true statement, when we multiplied both sides by the same negative value, we have to flip. Right? We have to flip. And so this would be a less than, and that would make it a true statement. So just keep that in mind as you're working these problems. Again, if you multiply or divide by the same negative value, you've got to flip the direction of the inequality in order to get the correct answer. All right, let's take a look at some sample problems, and we're going to use the same skill set we used from equations. Our goal is always to isolate x, whether we're solving an inequality or an equation. And again, we use kind of the same techniques here. So I have x plus 8 is less than 5. I want to isolate my variable x, so I want to isolate this guy. So all I need to do in this case is move 8 away. So to do that, I just subtract 8 from both sides of the inequality. So minus 8 minus 8. Very, very simple. Remember when we're solving equations like x plus 8 equals 5, I did the same thing. I just subtracted 8 away from each side, and I got a solution of x is equal to negative 3. Well, it's the same. I'm just isolating x, and I'm using pretty much the same techniques. So this will cancel. X is now isolated, and it's less than 5 minus 8 is negative 3. So what we're saying is that x can be any number that is less than negative 3, and I'll get a true statement. All right, so let's write our solution using interval notation. And in most cases, this is what your teacher is going to expect you to do. So the smallest value that x can take on is really negative infinity, right? Because x can be anything less than negative 3. So we'll write negative infinity. And remember, we put a parenthesis next to that because it's not included, comma, and then what's the largest value x can take on? Well, it's got to be less than negative 3. So it can be any value up to, but not including negative 3. So we'll put negative 3 there. And then again, we'll put a parenthesis there to say that negative 3 is not included. So let's graph this real quick. I'm going to take these down here. And graphically, x is less than negative 3. You find negative 3 on your number line. I'm going to put a parenthesis facing to the left. And then I'm going to shade everything this way, including that arrow. So this is x is less than negative 3 graphically. Now, when we solved our linear equations in one variable, we always checked to make sure that we got the right answer. Checking a linear inequality in one variable is a lot more work. So the official way that you're going to check it is basically to use 3 steps. So the first thing you're going to do is you're going to replace your inequality symbols with equal symbols. So I'm going to change this x plus 8 is less than 5 to x plus 8 equals 5. And I'm going to change x is less than negative 3 to x equals negative 3. So I'm going to make sure that this is the solution. Okay? So I'm going to take this negative 3 and plug it in for x. So negative 3 plus 8 does equal 5. So that checks out. So this is referred to as our boundary. Now, the boundary is going to separate the solution region from the non-solution region. And graphically, you can kind of see that negative 3 is the cutoff. Anything less than negative 3, anything over here works. So this is your solution region. Then anything starting at negative 3 and beyond doesn't work. So this is your non-solution region. So what we need to do after we establish the boundary, we need to take a number from the non-solution region and try it, and then also a number from the solution region and try it. So from the non-solution region, the easiest number to try is 0. So let's go back up here, and we can plug in a 0 for x, and we'd have 8 is less than 5. So that's in the non-solution region, so it should be false, and it is. So it's okay that this is false. That's what we want. Now, the next thing we're going to do is we're going to pick a number from the solution region. So that's over here. That's anything less than negative 3. So I can pick anything I want. So let's say negative 5. So I'd plug a negative 5 in for x. I'd have negative 5 plus 8 is less than 5. Negative 5 plus 8 is 3. And 3 is less than 5. So that's true. And that's exactly what we want because we picked a number from the solution region. So again, a lot more complex to check your answer here. So I'm not going to do it moving forward. It's something that you can refer back to this procedure and you can check it on your own because it is extremely time consuming. All right, let's take a look at the next one. So we have x plus 2 is less than or equal to 1. So to solve this, I'm just going to subtract 2 away from both sides of the inequality. This will cancel. I'll have x by itself. And I'll have less than or equal to 1 minus 2 is negative 1. So this is my solution. X is less than or equal to negative 1. And to write this in interval notation, again, the smallest possible value, we're dealing with a less than or equal to, so the smallest possible value is negative infinity, right? Because there is none. It continues forever and ever in the left direction. And then the largest possible value is negative 1. And because there's a non-strict inequality here, negative 1 is included. So I'm going to use a bracket there. So graphically, this is going to look like this. At negative 1, I'm going to put a bracket facing to the left, and I'm going to shade everything to the left, including that arrow. So this is x is less than or equal to negative 1. All right, let's take a look at 7x is less than 28. So if I want x by itself, I need to divide both sides of the inequality by 7. Now remember, I'm dividing by a positive number, so I keep the direction of the inequality the same. This 7 cancels with this 7, and I'm just left with x, and then is less than 28 divided by 7 is 4. So that's my solution. X is less than 4. So in interval notation, it's a less than, so the smallest possible value is negative infinity, right? Because it continues forever and ever and ever in the left direction. Then the largest possible value, it's not quite 4, right? Because 4 is not included, but we're going to put 4, and then we're going to put a parenthesis next to that to say, hey, we can go all the way up to any amount that's close to 4, but we can't actually get to it. So again, this parenthesis is telling me that 4 is not included. Now let me just make those even heights. And let's graph x is less than 4. All right, so I'd find 4 in the number line, and that's right here. I'd put a parenthesis facing to the left, and then I'm going to shade everything to the left. Shade all this, and shade the arrow to say, hey, x is less than 4. So it can't quite be 4, but it can be anything less. All right, let's take a look at negative 6x is greater than 30. Now I want x by itself, and in order to get x by itself, I need to divide both sides of the inequality by the coefficient of x, which is negative 6. Now, again, I'm dividing by a negative. If I multiply or I divide by a negative, I've got to flip the direction of the inequality. So do that first so you don't forget. So right now it's a greater than, it needs to become a less than. So you flip it. Flip. Very important. So this will cancel with this, and I'll just have x. And then 30 divided by negative 6 is negative 5. So x is less than negative 5. When we think about this in interval notation, we know there's no possible way to get a smallest value, right? So we're going to use negative infinity for that, because the solution continues to go to the left forever. And then for the largest possible value, I'm going to put negative 5, and then I'm going to put a parenthesis next to it to say, hey, negative 5 is not included. Now graphically, when we look at this solution, so I'm going to find negative 5, I'm going to put a parenthesis there, and I'm going to shade everything to the left, including that arrow, to say, hey, negative 5 is not included, but everything to the left is. And so x is less than negative 5 is the solution. Now, I know it's a little time consuming, but I want to show you this. It's very, very important. If I was to check this, let's say that I did not flip the inequality. Let's say that I went through, I didn't flip this, and I ended up with x is greater than negative 5. Let's say I said this is the solution. It's not, but I'm going to say I forgot to flip. All right. If you were checking this, the first thing you would do again is you would replace all your inequality symbols with equal symbols. So in this case, forget that this exists right now. This is gone. Just forget about it. I would have negative 6x equals 30 as kind of the original thing. Then the solution is x equals negative 5. Okay. So if I plug a negative 5 into x, I'd have negative 6 times negative 5 equals 30. So that works. So I know that I have negative 5 as my boundary. And again, what that means is it separates the solution region from the non-solution region. Graphically, and again, let me kind of erase this because we're kind of thinking about how to determine we have the wrong answer. Graphically, if I look at negative 5, if I came up with the wrong answer and I said x is greater than negative 5, I'd be thinking about, okay, anything larger than -5 would be in the solution region. And anything less than -5 would be in the non-solution region. So if I try something like 0, which should be in the solution region, I'm going to find that I'm going to get the wrong answer. Because again, I forgot to flip, and 0 is greater than -5, so that works out here. But in the original inequality, which was -6 times x, so I'd plug in a 0 there, is greater than 30. Well, -6 times 0 is 0. That's not greater than 30. This would be false. So that would be your first indication that something went wrong. I checked something that should have been in the solution region, and it didn't work, right? It did not work. So at that point, I'd go up here and go, okay, this is false. This doesn't work. This doesn't work. So I would go back and say, okay, well, I forgot to flip the inequality. So it's very time consuming to check, but when you first start doing these, you might want to, just to avoid making the errors. And let me show you what happens if you do this correctly. I know this is time consuming, but I feel like it's very important. So let's say I didn't forget to flip. We go back to our original solution. So x is less than -5. So we know our boundary is that x equals -5. So anything less than -5 should work as a solution, right? So if I plugged in a -10 for x, that's less than -5, that would be in my solution region. So it should give me a true result. So -6 times -10 should be greater than 30. -6 times -10 is 60. That is greater than 30. That's true. So that works out. That's exactly what we wanted. So if I use something like +10, that should not be a solution. So I'd have -6 times 10 is greater than 30. -6 times 10 is -60. That's not greater than 30. That's false, right? So that's exactly what we want. That's okay, right? Again, when you're checking this stuff, and I have to reverse this because I gave you the scenario where we got the wrong answer. When you graph this, anything less than -5 is in the solution region. Anything that's -5 or larger is in the non-solution region. And again, -5 is your boundary. It separates the solution region from the non-solution region. And that's why you establish that. So you can say, okay, I'm going to pick something on the non-solution and see if it works. It shouldn't, right? Because it shouldn't be a solution. And then I'm going to pick something on the solution region, and that should work. And when we plugged in 10 is in the non-solution region, it didn't work. That's what we want. When we plugged in something from the solution region, we tried -10, it did work. And that's what we want. All right, I know this video is kind of long, but when you first start out doing these, it's very important to get all the basics down, so it's kind of worth the time, even if you have to break it up. So we're going to look at one final problem here. We have -1/3 x is greater than or equal to 2. So if I want to isolate x and I have a fractional coefficient, we know what to do. We multiply both sides of the inequality by the reciprocal. So the reciprocal of -1/3 is -3/1. And remember, we're multiplying by a negative. So we gotta flip this. So this is going to go this way. So instead of greater than or equal to, it's now less than or equal to. This is going to cancel, and I'm just going to have x is less than or equal to 2 times -3 is -6. So x is less than or equal to -6. Let's do the interval notation for that. So it's going to be -infinity over here on the left, right? Because we're not going to have a smallest possible value. So we use -infinity. And then for the largest possible value, we're going to use -6. And that's included because this is a non-strict inequality. So we're going to use a bracket next to -6. Now graphically, I'm going to find -6, and I'm going to put a bracket there facing to the left. And I'm going to shade everything to the left. And I'm saying, hey, -6 is a solution. That's why I got the bracket. And then anything to the left is also a solution.